So we've been talking about modular arithmetic and this idea that we can work modulo some number. And the punchline for that, remember, is to take the totality of all the integers, infinite number of them, and reduce ourselves to a small set, a finite set of integers, and be able to make statements about all integers based on statements we make on a small set of integers. And it's similar to what happens in 250 when we work with binary systems. We can prove theorems with truth tables in 250 because we can enumerate all the possibilities because everything's a 0 or a 1. Whereas to prove a theorem about integers, we can't really do that with a truth table unless we had a table containing every possible value of every integer. So we can do things like this. Suppose you want to know if a number is divisible by 3. So let's just pick a random number. So 73,245. It's a 5-digit number. We want to know if it's divisible by 3. Now we can divide this by 3, right? Do long division and carry the remainders and all that kind of stuff. But we can also do the following. So let's concentrate on modulo 3. So if something's divisible by 3, what's it congruent to mod 3? 0, right? That's a handy way of defining divisibility. Congruent to 0 mod n means you're divisible by n. Well, let's look at this number, 73,245. This is the number 5 plus 4 times 10 plus 2 times 10 squared plus 3 times 10 cubed plus 7 times 10 to the 4th. Agreed? That's what we mean by decimal numbers. And to know if this is divisible by 3, we need to know if this sum is divisible by 3. And so if we can find what this is congruent to modulo 3, we'd know what 73,245 is congruent to mod 3. Well, 5 is congruent to 5. Plus 4 times, but what is 10 congruent to mod 3? 10 is congruent to 1. So 4 times 10 is congruent to 4 times 1. And what is 10 squared congruent to? Yeah, did you do 100? Yeah. So 100 is congruent to 1, but since 10 is congruent to 1, 10 squared is congruent to 1 squared, which is 1. And this is the rhythm we want to get into, right? We can start saying things about big numbers by saying things about smaller numbers that are congruent to them. So since 10 squared is congruent to 1, 2 times 10 squared is congruent to 2 times 1. And 10 cubed is congruent to what? That's also congruent to 1. And 10 to the 4th. And in fact, 10 to any power is going to be congruent to 1 because it's congruent to 1 to the n, which is just 1. So 10 cubed is congruent to 1, and 10 to the 4th is congruent to 1. So this original number is congruent to 5 plus 4 plus 2 plus 3 plus 7. In other words, that number is congruent to the sum of its digits. And there's nothing magic about that number. I just didn't want to use variables, so I picked a particular number. But it's arbitrary. So 5 plus 4 is 9, plus 2 is 12. 5 plus 4 is 9, plus 2 is 11, plus 3 is 14, plus 7 is 21. Is 21 divisible by 3? Yes, so this number is also divisible by 3. And that works for any integer. Add up the digits. If the result's divisible by 3, the whole thing is divisible by 3. And if you don't like adding big numbers, 5 plus 4 is 9. Well, that's divisible by 3, so I'll just call that 0. 2 plus 3 is 5. That's 2 more than a multiple of 3, so I'll call that 2. 2 plus 7 is 9. 9 is divisible by 3. So I never even have to add anything more than some one-digit numbers. even if I had 15 digits in my number. So you can do this in your head pretty quickly and tell whether or not a number is divisible by 3. Now what if we were to work modulo 9? This is 5 plus 4 times 10 plus 2 times 10 squared plus 3 times 10 cubed plus 7 times 10 to the 4th. Well, what is 10 congruent to modulo 9? 1. So what's 10 squared? 1. What's 10 to the nth? 1. Same thing happens. This is congruent to 5 plus 4 plus 2 plus 3 plus 7. 5 and 4 is 9, 2 is 11, 3 is 14, 9 is 21. Is 21 divisible by 9? No. So this number is not divisible by 9. But this number is, because if I add up the digits there, I get 27, and 27 is divisible by 9. So guarantee this number is a multiple of 9. This is called casting out 9s or casting out 3s. It's just a trick, but it's a use of modular arithmetic, a particular use, where we can say something about this large number by just saying something about the individual digits. So have you seen this before, casting out 9s? So let's look at one more. Let's look modular 11. So modular 11, what is 10 congruent to modulo 11? It's 10, obviously, but what else is it congruent to? -1. It's 1 less than a multiple of 11, which means 10 squared is congruent to 1. 100's 1 more than 99. 10 cubed is going to be congruent to -1 cubed, which is -1. So 1001 is a multiple of 11. It's 7 times 13 times 11. 10 to the 4th is congruent to +1, and so on. So the even powers of 10 are congruent to 1. The odd powers are congruent to -1. So this original number, 74,236, is congruent to 6 plus 3 times -1 plus 2 plus 4 times -1 plus 7, which is equal to, or congruent to, 6 plus 2 plus 7 minus 3 plus 4. So we can tell whether a number is divisible by 11 by doing the following trick. Add up all of the odd positioned numbers, digits 1, 3, 5, 7, 9, and so on. Add up all of the even position numbers, 2, 4, 6, and so on. And if the difference of those two sums is divisible by 11, then your number is divisible by 11. So those are just parlor tricks, but they illustrate the fact that we can say things about numbers by looking at what they do modulo other numbers. All right, well, let's see another version of this. This is something called modular exponentiation. So suppose we wanted to calculate So this is just an example. So let's calculate 7 to the, I don't know, 7 to the 43rd modulo 5. So we want to take 7, multiply by itself 43 times to see what the remainder is when we divide by 5. And we don't want to actually calculate 7 to the 43rd and then look at the last digit, because that's a lot of work, and 7 to the 43rd is a big number. And we could say 7 is congruent to 2 and then calculate 2 to the 43rd modulo 5, but that's also a lot of work. That's 43 multiplications and divisions and simplifications. But here's a different way to calculate powers like this. So write 43 in binary, or as a sum of powers of 2. So it's 32 plus 8 plus 2 plus 1. Yes?
Are we doing it in binary because 7 multiplied 5 is 2?
No, we're always doing it in binary. So because we want powers of 2, multiples of 2, that when added together give us our exponent. So write the exponent in binary. I didn't actually write it in binary, I could. What we really want is to know which powers of 2 add up to 43. And now we're going to do a series of calculations. So 7 to the first is congruent to 2, because it's 2 more than a multiple of 5. 7 squared is congruent to whatever 7 to the first is squared. So it's 2 squared, which is 4. 7 to the fourth is congruent to this thing squared, 4 squared, which is 16, which is congruent to 1 mod 5. It's 1 more than 15. 7 to the eighth is congruent to 1 squared, which is just 1. 7 to the 16th will also be 1. 7 to the 32nd will also be 1. All right, so however many powers of 2 I need to be able to express 43, that's how many times I have to calculate 7 raised to these powers of 2. So 7 to the 1st, 2nd, 4th, 8th, 16th, and 32nd. And in this case, it got really easy because once I had a 1, keep squaring that, I'm going to keep getting a 1. But even if not, this is not a lot of work. So 7 to the 43rd is actually 7 to the 32 plus 8 plus 2 plus 1. And you remember how exponents work when you have exponents added together, how you can rewrite that? Yeah, so adding exponents multiplies the individual pieces. So this is congruent to 7 to the 32nd times 7 to the 8th times 7 squared times 7 to the 1st. And 7 to the 32nd is 1. 7 to the 8th is 1. 7 squared is 4. 7 to the 1st is 2. That's congruent to 8, which is congruent to 3, and we're done. So by writing our number as a product, as a sum of powers of 2, we can write 7 to the 43rd as 7 raised to a set of powers of 2 added together, which law of exponents says we can just multiply each of these together. And we can calculate 7 to each of these powers by doing this operation over here where we just keep squaring the next lower power. And then we have a few very simple multiplications to perform. And we reduce the final product modulo 5, which in this case gives us 8. Yeah. So 7 squared is 4, so 7 to the 4th is 4 squared, which is 16. And 16 is 1 more than a multiple of 5. Right, so we're doing all of this mod 5. Mm-hmm. machine's a little hosed. So there's 7 to the 43, and you can see the last digit is a 3, so we know it's 3 more than a multiple of 5. So we in fact got the right answer. All right, do you want to try a different one of those? So let's find 3 to the 17th modulo 7. So 3 to the 17th equals 3 to the 16 plus 1. Which we're actually thinking of 2 to the 4th plus 2 to the 0. 16 plus 1. So let's write down what powers of 3 are mod 7. So 3 to the 0 is just 1, so that's congruent to 1. 3 to the 1 is just 3. 3 squared is congruent to what? 9, which is congruent to 2 mod 7, good. 3 to the 4th is congruent to 27. That would be 3 to the 3rd. Yeah, so 3 to the 4th, we just have to square 3 squared, which is 2 squared, which is 4. 3 to the 8th will be 3 to the 4th squared, which is 4 squared, which is 16, which is congruent to what? 2. And 3 to the 16th will be 2 squared, which is 4. And if we had to keep going, we've got a pattern now. Right? 4 squared is going to be congruent to 2, and 2 squared is going to be congruent to 4, and that pattern is going to keep repeating from that point forward. So filling these out is just kind of an exercise in writing, but we only need to go up to 3 to the 16th. So 3 to the 16th plus 1 is congruent to 3 to the 16th times 3 to the 1st. And 3 to the 16th is 4, and 3 to the 1st is 3. So this is congruent to 12, which is congruent to 5.
How did you know that 3 to the 16 is congruent to 2 squared?
Because 3 to the 8th is 2. So 3 to the 16th is 3 to the 8th squared. So you just keep squaring the previous answer you found. So 3 to the 17th is this. 3 to the 17th divided by 7 is this. But 3 to the 17th minus 5 divided by 7 is a nice integer. And this is so much less work, right? If we wanted to calculate 3 to the 1000th, right, we fill out this table up through 512, and then we just multiply the proper terms for whatever powers of 2 add up to 1,000. And it's no more than 9 multiplications we have to do, as opposed to doing 1,000 if we just kept multiplying 3 by itself. Yeah?
Why isn't it 3 mod 7 -4?
It is. So this is also -4. So 3 squared would be -4 squared, which is 16, which is still 2. And you should always be able to choose whatever number you want and get the same answer. So that's a good exercise, good test on it.
But it's not saying 3 mod 7 is -4, but 3 is congruent to 4 mod 7.
3 is congruent to -4 mod 7, yes. So 3 squared is congruent to -4 squared mod 7. And you can do this with anything that's equivalent to these things mod 7. But if we pick that particular number between 0 and 6, right, then we're minimizing our amount of work. But sometimes picking a minus 1 is useful. Right, if something's congruent to 6, we could replace that with -1, and now we can take the powers pretty easily, because it's just going to be 1 and -1. All right, so you got the idea of modular explanation. There's some homework questions to practice that. Let's talk about primes. So what's a prime number? A number whose only factors are itself and 1. And for technical reasons, 1 itself is not considered prime. So the smallest prime number is 2, because it's only divisible by 1 and 2. 3, 5, 7, 11, 13. And so on. Those are all prime numbers. 6 is not because it's 2 times 3. 8 is not because it's 2 times 4. 9 is 3 times 3, and so on. And you can see some consequences of this pretty quickly. Most prime numbers are going to be odd, because even numbers are divisible by 2. The only exception is the number 2 itself, which is prime, bless you. But the other even numbers are composite, not prime. And there's no multiples of 3 that are prime except for 3 itself. And there's no multiples of 5 that are prime except for 5 itself. And so on and so forth. So composite means not prime. Composite as in composed of other numbers. So there's a theorem, it's called the fundamental theorem of arithmetic. Which makes it sound pretty important, which it is. So the fundamental theorem of arithmetic basically says that any number can be factored uniquely as a product of primes. So let's say positive numbers, positive integers greater than 1 can be factored uniquely with a footnote into a product of primes. What's the footnote? Ignoring the order. For example, 6 can be written as 2 times 3. It can also be written as 3 times 2. Does that violate the fundamental theorem? No. 2 times 3 and 3 times 2, we consider those to be the same factoring. But if we could also write 6 as 5 times 7, that would violate the fundamental theorem. So the fundamental theorem says if you take a positive integer, you can write it as a product of primes, and that set of primes is essentially unique, other than rearranging the order in which you multiply them. If the number itself is prime, then it's just equal to itself. That's its unique factoring. So 7 is just 7 times nothing. But 14 is 7 times 2, 35 is 7 times 5, 128 is 2 times 2 times 2 times 2 times 2 times 2 times 2, and so on. So this means we can write any integer n, which is bigger than 2, bigger than or equal to, as n equals some first prime raised to some power times some second prime to some power times some third prime to some power times some kth prime to some kth power. And it's no difference from just writing, p1 n1 times, p2 n2 times, and so on. But we usually write it in terms of powers of primes because it's a little easier to manage. And the fundamental theorem, right, is the statement that this factorization is essentially unique. And that's not always the case. It's always the case for integers, but it's not always the case for other systems. For example, suppose we think about this. This is a funny way of writing the set of integers that also include the square root of minus 1. So this is a bigger set than just the integers. It's still countable. But it's a set of all integers plus the square root of minus 1. So this is still an integer, but so is this. And so is this. And it turns out that if these things are integers, if we multiply these together, we get 4 plus 2i minus I squared. I squared is minus 1, so this is minus 1 is plus 1, which is 5. This is no longer prime because we can write it as a product of two other things that are in our extended set of integers. And in some cases, we can find extensions to the integers where we don't have unique factorization, where we can express what it means to be a prime, but we can find things that are a product of different sets of primes. That was one of the gotchas on a proof of Fermat's last theorem, done by someone named Kummer in the 1800s, I believe. And he assumed that when he had this extended set of integers, he still had unique factorization. And he was able to prove Fermat's theorem. And someone pointed out that you don't have unique factorization in this set that he was working with. It's called a ring of integers. And he developed a branch of mathematics called ideal theory by trying to correct that situation. So for us, life is good. We always have unique factorization. So we have the fundamental theorem of arithmetic. And we'll use that in a few ways. All right, so how do we test for prime numbers? How do we tell if a number is prime? If mod whatever, what's whatever? So okay, so here's the 1001. We want to know if it's prime. We can see what is congruent to modulo 2, modulo 3, modulo 4, modulo 5, all the way up through modulo 1000. And if any of those are congruent to 0, then it's divisible by something that's not prime. And if and only if we try all of those cases and it's not divisible by any of them, then we can say this number is prime. There are other ways, but that's one way. This one, we have our even odd digit trick. The sum of the odd digits is 1. The sum of the even digits is 1. That's the same. Their difference is 0. This is going to be divisible by 11. So this equals 7 times 11 times 13. So it's definitely not prime, but it looks kind of prime. 101, on the other hand, is prime. Now, if you try dividing by every number smaller than that, that will tell you if it's prime or not. That's a lot of work. If this number is divisible by something like 90, then when we divide it by 90, we would get something pretty small, right? And so you really don't have to go above half of this number. Because if we divide this by something bigger than half of it, we're going to get something smaller than half of it. And we would have already found that on the way. So we can cut our search in half by only searching up to this number divided by 2. But we can actually do better than that, too. What do we have to search up to? The square root. Because if 101 equals a times b, and a is bigger than the square root of 101, b is going to have to be less than the square root of 101. Let's make them equal. And so if a is bigger than the square root, and that's a factor, we would have had a factor b that was smaller than the square root. So we really only have to check up to and including the square root in the number, which is a big time savings. So you'll be playing with primes for your second programming assignment in here. So that's a useful embellishment. Because if you're looking to numbers around 1,000,000, and you check every number up to 1,000,000, that's 1,000,000 operations you have to perform. If you check up to the square root, it's only 1,000. So it's going to be 1,000 times faster to use this restriction. So that's one way to check for primes. It's just called trial division. Now here's another approach. This is called the sieve of Eratosthenes. I'm not going to try to spell it. Here's the idea. Write down your integers. I don't know how far I want to go. Go up to 30. Go up to 31. All right, write down your integers. Start with the number 2. Circle that, and then cross out every other number. So every second number gets crossed out. Circle the next number that's not circled yet. That's a prime. Cross out every third number now. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. Circle the next number that's not crossed out or circled. That's a 5. That's your next prime. Cross out every fifth number. 10, 15, 20, 25, 30. And keep going. There's a 7. Cross out every seventh number. Next number that's not circled or crossed out is 11. Cross out every 11th number. Circle a 13. Cross out every 13th number. And you just keep going. And this will get you all of your primes. So we cross off 34, there's 19, we'd cross off 38, there's 23, there's 29, there's 31. So it's like a sieve that you use to pan for gold or something, right? The water falls through and the gold nuggets are left because they're caught by this mesh. That's basically what's happening here. So when we cross off every nth number, right, we're saying that's not a prime. And when we're done with this, what's left are just the prime numbers. Yeah, that should be pretty straightforward to prove, because if something's not prime, it's divisible by some number smaller than it, and it would have gotten crossed out when we wrote out all the multiples of, when we crossed out the multiples of that factor. Yeah, it's enticingly straightforward. It seems like there's more there. All right, so this came up earlier. So how many primes are there? there's certainly a lot. We've found primes with millions of digits. But are there an infinite number of primes, or do they vanish after some point? So you're nodding your head. Infinite number of primes. So yeah, so it's a countably infinite set, right? It's the same as the integers or the evens and odds, but it is infinite. And this can be proven, and this proof has been known for thousands of years. We can use a proof by contradiction. So prove there are an infinite number of primes. Okay, proof by contradiction. Suppose P is the largest prime. Okay, so we're going to assume there's not an infinite number of primes, which means there is a largest prime. Right? Not an infinite number means there's only some finite collection of primes, and in a finite set of integers, we can find the largest integer. So let P be the largest prime. So let's number our primes, P1, P2, P3, Pn, which is our last prime. Let this be the set of all primes. Well, let X be the product of all those primes plus 1. All right, so X is the product of all known primes, all primes that exist, plus 1 more. Well, what is X congruent to modulo P1? It's 1 more than a multiple of P1. It's P1 times all of this stuff plus 1 more. So X is congruent to 1 modulo P1. What's it congruent to modulo P2? What is this congruent to modulo P2? P1 times P2 times P3 times Pn. That's congruent to 0 modulo P2. So if we add 1, that's also congruent to 1 modulo P2. In other words, this expression here is 1 more than a multiple of P2. It's P2 times the product of all those other primes plus 1 more. And in fact, X is congruent to 1 modulo P anything. It's congruent to 1 modulo every prime number. Well, if you're congruent to 1, then you're not divisible by the thing that you're congruent to 1. If you're congruent to 1 modulo P1, X cannot be divisible by P1. It can't be congruent to both 0 and 1. And it can't be divisible by P2. It can't be divisible by any of these P's. So X is not divisible by any prime. Therefore, X is prime. But X is bigger than the largest prime, which was Pn, because it's Pn multiplied by a bunch of other stuff plus 1 more. So there's a contradiction. And therefore, there is no such P which is the largest prime. So it must be that there's an infinite number of primes. So that's useful. So questions on that? Yeah. What do you mean absolute?
I was, because I was
I'm not familiar with the terminology. You may have read more of that book than I have at this point. All right, so we have an infinite number of primes. A Mersenne prime is a particular type of prime number, is a prime that can be written as a power of 2 minus 1. And these are special prime numbers. Primes are special to begin with, but among primes, Mersenne primes are even more special. One less than a power of 2, which means in binary it's just a string of ones, which is kind of cool. So for example, 2 squared minus 1 is equal to 3. That's prime, so that's a Mersenne prime. 2 cubed minus 1 is equal to 8 minus 1 is 7. That's another Mersenne prime. 2 to the 4th minus 1 is 15. That's not a prime number. 2 to the 5th minus 1 is 31. That's another Mersenne prime. 2 to the 6th minus 1 is 63. That's divisible by 3, so it's not a prime. 2 to the 7th minus 1 is 127, and that's also a prime. And you may notice that in the cases where the result is prime, the exponent itself is also prime, which can lead you to wonder, if we take 2 and we raise it to a prime power and subtract 1, do we always get a prime? And you don't, unfortunately. It's not always prime, but if 2 to the n minus 1 is prime, then so is n. So that's a really painful way to check if n is prime, see if 2 to the n minus 1 is prime. But that's kind of going backwards.
So 2 to the prime minus 1 isn't always prime.
Right.
But if 2 to the n, okay, so like the other way around.
Yeah. If we have a Mersenne prime, then that exponent itself must be prime. And so Mersenne primes have been studied for a long time, and it's Mersenne primes that make up the largest known primes for us, the primes that we know of. The largest ones are always Mersenne primes because we have techniques for testing whether or not this is prime that don't involve dividing by every possible number less than its square root. There's faster ways. There's something called the Lukas-Lemur test. It's a really popular approach, and lets us do this determination pretty quickly. I don't seem to have. There we go. My laptop is just trashed. I don't know what the problem is. And the network's trashed. We'll give it a minute. I think this will give us a list. Yeah, so the largest Mersenne is 2 to the 277 millionth, minus 1. And there aren't that many Mersenne primes. They spread out really drastically. Prime numbers themselves tend to spread out, right? 2, 3, 5, 7, 11, right? That's almost every other odd number. Every odd number, right? Every other integer. But when you get up to much larger numbers, the distance between primes starts to increase, and they become increasingly pair. So here's all the Mersenne primes that we know about. And there's the corresponding prime number here that you raise 2 to that and subtract 1. So those first few were known thousands of years ago. 2 to the 13th was discovered anonymously. Someone didn't want to know. They did it by trial division. 2 to the 17th, 19th, and 31st done by trial division. And then we started using these Lukas-Lemur tests down here. And these numbers started growing really quickly in the mid-1900s. And then end of the century and this century, we've just kind of taken off. So people dig this stuff. And these solutions over here, they say GIMPs. So GIMP is the Great Internet Mersenne Prime Hunt, right? And it was a way to basically, instead of running a screensaver on your PC, you could download a power of a prime number and test it to see whether it was prime. And so people all around the planet had their PCs just kind of working on different numbers to see if they were prime, and they would send their results back to a central server. And that's how most of these larger Mersenne primes have been discovered. It's just been crowdsourced since the mid-1990s. And so this was the latest Mersenne prime. This was just discovered the day after Christmas, I guess. And it's got 23 million digits to it. And you can find that expanded out somewhere on the net if you want. Yeah, totally. That would be pretty cool. Yeah, so 3.3 gigahertz Intel. Cool. All right, so we'll talk more about prime numbers tomorrow. We'll talk about the prime number theorem, which is cool, and then we'll talk about some open problems in primes, which will take us into your second programming assignment.